All right, so this is a follow-up on the previous lecture. We're still talking about stress transformation, but instead of talking about it using some of those sort of confusing stress transformation equations, right, which came from looking at this stress cube, sort of in the left-hand side here, taking a cut at a specific angle, and then summing forces both perpendicular to the cut and in the direction parallel to the cut, all right, as we did before. And we actually ended up, I'll show you here, with these final stress transformation equations, right? Sigma xx, sigma yy, tau xy, all primes, so those are all not the original xy, but a new xy coordinate system. And all the sigma xx's and sigma yy's that are on the right side of these equations, those are all the stresses that are defined in the original coordinate system. Okay, so what we're going to do now is take a different look at those equations. And it was Mohr who first noticed this, but he said, you know, those equations are actually the equation of a circle, right? And a couple things to note, that the center of the circle, right, is actually this sigma xx plus sigma yy divided by 2, 0, right? So that's where this circle is centered, right? And that honestly is nothing more than the average normal stress, right, at any point, right? And then the radius of the circle, r, is just this other term, sigma xx minus sigma yy divided by 2 is squared, plus tau xy squared, and then we take the square root of this entire thing. Sneak it in there, there we go, right? So actually, let me try that one more time. You know what? Let me give myself a little bit more room there. Sorry about this. So the radius is now sigma xx minus sigma yy divided by 2, that quantity squared, plus tau xy, quantity squared, and then square root of that whole thing. Like that. Okay. So that's the center and that's the radius. So effectively what you can do is go ahead and plot, I guess I'll do it in, well, let me do it in blue to start. So let's say this is the center, right? So this guy here is, I'll say sigma average, 0, right? And then we're going to get some radius here, right? So that radius, let's say it goes to this point here, that's going to be r, right? And then, given the center of the circle and the radius, right? See if, yeah, okay, more or less. Well, let me try that one more time. So this is my radius, and like that, okay? So that is my circle. It's known as Mohr's circle, right? And it effectively plots out all combinations of sigma and tau on any face on the cube, right? So I know that sounds very confusing, but effectively what it means is that if I came in here to sort of an arbitrary point right there, right? Let me get rid of this guy. Right there, that the sigma associated with that point and the tau associated with that point occur on some orientation of the cube. Okay, so that's basically what it means. And a couple things I need to point out here. One is that the sigma, the normal stress, is positive to the right, and the other, and this is really important, your book does not do it this way. I don't know why. I think it makes it way more confusing. But I'm plotting the positive shear stress downward. I know that's confusing to you. And it turns out that if you plot the positive shear stress downward, then a clockwise rotation on the Mohr circle will be equivalent to a clockwise rotation on the cube, right? So they're physically the same. I think the way your book does it is says a clockwise rotation on Mohr circle is a counterclockwise rotation on the cube. And I think, at least in my experience, that has made for some very confusing, sort of calculations and a lot of potential for error. The other thing I've got to point out is that on this circle, 2 theta is the angle, sort of measured just counterclockwise, sort of right-hand rule measurement. And that is equivalent to theta on that cube, right? So if I rotate on the circle, let's say from this point here, right, to that point over here, right? So that is a 180-degree rotation, right? That is equivalent to a 90-degree rotation on the stress cube over there on the left, okay? Okay, so I think we've got everything that we need for me to explain how to plot this. You can, in fact, just start by calculating the center of the circle, that's shown there in red. You can also calculate the radius of the circle, right? And then you can get your compass out, put it at the center, change the dimension of it until it equals the radius, and then draw a circle, right? And that will tell you all of the points that are on the, that if I, no matter what orientation of the cube, I can generate those stresses, right? That is useful, but it's not the most useful way. And there's a few things that you're missing if you do it in that way. And primarily what you're missing is the relationship between where we are on this circle at any given orientation of the cube, okay? And so what we're going to do is I'm going to walk you through kind of how I plot these, the Mohr circle, and hopefully it will start to give you a better sense of what this Mohr circle actually is and how to use it. And again, next time we'll start talking about principal stresses. After that, we will start doing a bunch of examples where I show you how to plot Mohr circle for various stress distributions, stresses at a point, and then we can orient them and calculate, what are the principal stresses and what are the orientation of those principal stresses, etc., etc. Okay, so let's jump into this. So if I have my stress cube here, right, this is my coordinate system, right, x and y. And this is my sigma xx and my tau xy, right, that look just like that. And this guy up here is my sigma yy, right? All right. So the first thing I'm going to do is I'm going to plot these guys, these 2 points, right? So that is a positive tau xy, right? And that is a positive sigma xx, right? In fact, why don't let me do this. Let me erase the circle that's here. You'll see we're going to end up with pretty much exactly the same circle, but I'm going to show you a different way of doing it, and one that hopefully will become more intuitive. Okay, so we're going to plot this tau xy and sigma xx. So let me say that it's located somewheres here. Right. So this is sigma xx, and this is tau xy. Right? Now notice that the tau xy is positive, and I'm plotting it below the sigma axis, the x-axis, right? And that's because tau is positive downward, right? And again, if we do not take it as positive downward, a clockwise rotation on the stress cube there is going to be a counterclockwise rotation on the Mohr circle, right? So we got to make sure that if we do it this way, they have the same, the same direction of the rotation. Okay, so that's step one, right? Then step two is we are going to define a new coordinate system. This coordinate system, I'm going to draw them right next to one another here. But this is going to be x prime, y prime. Okay, and so what you've noticed, hopefully, is that I took this xy coordinate system and I rotated it counterclockwise 90 degrees. So instead of x pointing to the right, it's pointing up, and instead of y pointing up, it's pointing to the left. Right? And now what I want to do is I want to plot these guys. Right? And in fact, what I'm going to do is I'm going to erase this, and I'm going to write that sigma xx prime equals sigma yy. Right? So if I've defined my new coordinate system by rotating it, what has happened is that sigma yy is now pointing in the x prime direction, and it becomes sigma xx prime, right? And then the tau xy actually becomes negative tau xy, right? So how do we think about that? Well, I've now I've rotated my coordinate system 90 degrees, and now if you look at that arrow, right, and I'm going to go over it maybe in, I can't go over it in blue, it's already blue, let me go over it in green. All right, so it's pointing now in the minus y prime direction, and it is acting on a positive x prime face. So that is what we are going to call a negative shear stress, right? So this is about the only thing that you can sort of screw up if we want to, sort of use those terms, right? So if we are going to plot this, right? So this point is here. Let me get rid of that, right? And what that point is actually sigma yy minus tau xy. Right? And the reason it's a minus tau xy is because I've rotated my coordinate system, and the shear stress that used to be positive on the y face is now negative on the x prime face. So once I've plotted those two, right, now I can connect these guys. Right? So I connect those points, right? And if you look, this guy here, the center of the circle, is actually sigma average, right? So I went, basically, if you look at them, I'm adding sigma yy plus sigma xx, dividing it by 2, right? And that gives me the sigma average, right? So let me actually draw that here. Oh, let me do that in, I guess I'll do it in black. So this is sigma xx plus sigma yy divided by 2, right? So that's that dimension, right? And then this guy here, if I'm going to keep going with this, is actually sigma xx minus sigma yy divided by 2, right? And then if you look, the entire dimension from here to here, right, that's just sigma xx. Okay? So if I add those two terms together above, it just ends up with sigma xx. And that's, of course, exactly what it is. Okay? Okay, so now that I've drawn these 2 points, right, they are 180 degrees apart, right? So this is 2 theta equals 180 degrees, right? So that means theta is 90 degrees. Well, that's exactly what I did. That's the difference between the red coordinate system and the green coordinate system. I rotated it 90 degrees, okay? Now I can draw my Mohr circle, right? So this guy looks something like, I'm going to see if I can get it to actually hit those 2 points. Oh, geez, I forgot to turn on my little cheating thing there. I think I can do a little better than that. Like that, okay. Boy, that actually looks terrible. Hold on. Let me see here. So I need to go through those points. There, that looks much better. So that's my Mohr circle, right? And what you can see is where we're starting, right? Where we're starting, that red dot is associated with the X face, right? And that this green dot here is associated with the Y face, right? Technically, it's associated with the X prime face, because if it was associated with the Y face, this wouldn't be a minus tau xy, it would just be a positive tau xy, right? But then you notice we actually don't get a circle, right? So, so that is our Mohr circle, and this dimension here, how do I want to do it? I guess I'll just do it like this. Oh. Blue. So this is the radius, right? And that is now 2 theta, right? 2 theta, all right? So that radius is right here, right? The center is right there, right? So it doesn't matter which way I plot it, I get exactly the same circle, right? The difference is now I know where I'm starting, right? So if I want to measure theta from the X face, right, then I actually need to measure it from here, right? So this is where I would start, right? If I want to measure theta from the Y face, well, I would start measuring in that direction, right? And any amount of rotation, so if it's 45-degree rotation on the cube, that means it's a 90-degree rotation on the Mohr circle, right? So that would define stresses that look, stresses that look like that, right? So they would be 90 degrees off. I know that doesn't quite look like 90 degrees, but that's the idea, right? They would be 90 degrees off, right? And let's see, a couple minor things I've got to point out here. So this dimension here, right, that is tau xy, right, as you can see right there, right? So I know this is sort of confusing, right? It's sort of a visual way of looking at these confusing stress transformation equations, right? The important parts that you need to remember, and again, I think a lot of the examples that we're going to do are going to help sort of flush this out a little bit for us. The first is that we're going to plot the stresses on the x face. Actually, the first is that we're going to plot tau positive downward. I know there's going to be a number of questions because people either aren't hearing me say it or they're forgetting. But tau has to be positive downward. If you plot tau positive upwards, you are going to completely confuse yourself because the clockwise rotation on the Mohr circle will be a counterclockwise rotation on the actual stress cube, right? But if I can plot tau positive downward, then the rotations are the same. So clockwise rotation on the stress cube is a clockwise rotation on the Mohr circle, right? So that's number one. Number two is that we start by plotting the, why don't I label them the way I just said it? So that's number one. Number two is that we're going to plot the stresses on the x face. Right? Those are the ones that are in red, right? Then number three, we are going to plot the stresses on the y face. And the only difference is that we're flipping the sign of the tau xy, right? And the reason that happens is because when we move from a xy coordinate system to a x prime y prime coordinate system, that's the transformation, right? The shear stress sign on the y face goes from positive to negative or negative to positive. It flips, right? And hopefully you can see that. That green arrow there is on a positive x prime face, but it's now moving in the minus y prime direction. Right? Okay, and once you do that, then you can go ahead and plot the entire circle, right? And then there's a lot of questions that we can answer with this circle, right? And I will label some of these things next time. Right, but that's effectively the what we are doing to get the Mohr circle. Right, so let me summarize this here. I'm going to call it steps for drawing Mohr's circle. Okay. So step one, in fact, why don't I just do it like this? So step one is we plot the stresses on the x face. Right? So these are, and I'll say in sigma tau space, right? So that is sigma xx, tau xy, right? So that is the red point here, right? Step two, right, is that we plot the stresses. I'm going to say x prime face, then in parentheses I'm going to say y face, right, in sigma tau space, right? And this is now sigma yy minus tau xy. And again, it's the minus because we are plotting it. Once we do this coordinate transformation to x prime face, the sign of the shear stress flips. The third is to connect points 1 and 2. So the point that we plotted in step 1 and the point that we plotted in step 2, right? That, by the way, is just sigma xx plus sigma yy divided by 2 times 0. That's the center. Right? If you connect those 2 points, it will cross the sigma axis at the center, right? The fourth is to calculate the radius of the circle, right? Right. So I'll say the radius equals a squared plus b squared, square root, right? Old Pythagorean theorem. And that is sigma xx minus sigma yy divided by 2 squared plus tau xy squared. So you probably will not remember that expression so easily unless you remember the Pythagorean theorem, right? If we go back to this, what you can see is the x direction or the sigma direction of, the dimension there is this guy. I might call it sort of x bar, right? And the y direction is y bar, right? Or the other way I could do it is I could call that A and that B, right? And then you can see the radius is just a squared plus b squared square root, right? So we're using these geometric relationships that we understand to remember some of these expressions that are really, quite confusing, right? So that is step 4, right? Step 5, do that here, is step 5 is to draw Mohr's circle and label sigma 1, sigma 2, and tau max, right? And we will go through this, but for the time being, I can show them here. Maybe I'll show them here in pink. So this is sigma 2. This is sigma 1. And those guys are tau max. Right? Notice that tau max and tau min are always the same because the circle is always centered on the sigma axis. Right? So if I wanted to summarize this, right, I would say that sigma 1 equals sigma average plus r. Right? Sigma 2 equals sigma average minus r. Right? So if you notice, I'm coming from the center of the circle and I'm moving an r distance to the right to give me sigma 1, right? Then I'm moving an r distance to the left to give me sigma 2. Those are respectively the maximum and minimum normal stresses. right? Those are the extents, the bounds of which the normal stress can be for this particular state of stress at a point. And then if you look at tau max is always equal to the radius of the circle, right? So tau max is always going to equal R, okay? All right, and then step 6, which is the last step, is to calculate the rotation associated with principal stresses in tau max, right? And it's basically this 2 theta equals the inverse tangent, right, of opposite over adjacent. Now let me clean that up a little bit. And we'll talk more about that next time, but effectively, right, if you're trying to find out what this theta is, you just take the opposite, right? So if I care about, well, I'll do this in pink quickly, and then if I care about this angle here, right, so how much do I have to rotate the x face to get to sigma 1, right? That's just going to be tau xy, right? So that's the opposite, right, over the adjacent, right, which would be this sigma xxyy, right? And then I would take the inverse tangent of that, and then I would divide it by 2, right? And let me just get rid of that. And the reason I'm dividing it by 2 is because it's actually 2 theta here on the Mohr circle, right, as opposed to just theta on the cube, right? So that's where that comes into it. Okay, so I think that's all I have for Mohr circle. Just quickly sort of going through this again. We're starting by taking these stress transformation equations that are really confusing and probably very difficult to memorize and employ without a mistake, right? And we're recognizing, or Mohr has recognized, that actually those plot out a circle in this sigma tau space, right? So it's not spatial dimensions, it's normal stress versus shear stress space, right? And that circle has a center at sigma average, or sigma xx plus sigma yy divided by 2, comma 0. So it's always centered on the normal stress axis. And then its radius is just a squared plus b squared over c squared, or sorry, a squared plus b squared equals c squared being the radius squared. So when I solve for that, I get the square root of this sigma xx minus sigma yy divided by 2 squared plus the tau xy squared, right? And so that plots out this circle. And this circle is a set of normal stresses and shear stresses at every orientation of this cube, right? So the 360 degree circle will plot out 180 degrees on the cube. So by the time I've turned that cube all the way 180 degrees, right, now I'm back to where I began, right? Because it's the same orientation that it was before, right? I'm just on the opposite face of it, right? Okay, so, and then the way to plot this is you start by plotting, you start by recognizing, again, that the shear stress is positive downward, right? Positive downward. Then you plot the sigma xx tau xy, right? So that those would be the stresses on the x face. Then you go ahead and plot sigma yy minus tau xy. The minus, again, because we're doing this coordinate transformation to x prime, y prime, and that flips the sign of the shear. All right. Hopefully you guys can see that. Once I connect those two, you see they cross the sigma axis at sigma average comma 0. Right? So that's the center of the circle. Then I can just, you can use a compass. When I was a student, a lot of people tried to do this graphically, right? It doesn't always work out perfectly. So the circle is there. The way I like to think about it, the circle is there is to get me to conceptually understand sort of where these stresses should be, right? For example, when I look at this, I can see that I better rotate this cube counterclockwise, probably about 20 some degrees, in order to get to sigma 1, my principal stress, right? And that's just because when I'm looking at it on the Mohr circle, I can see that the sigma xx tau xy point is about 45 degrees, right, from where that sigma 1 is, right? So if I rotate 45 degrees around the circle, I get to sigma 1, and that's twice what I have to rotate the my stress cube at, right? So it sort of gives me this ballpark. I can look at it and go, geez, okay, if sigma 1, well, I didn't put any numbers down, but when we put numbers down, you'll see you can ballpark your principal stresses. You can ballpark the angles, you can ballpark the tau max, right? And then when you calculate it, because you'll be a lot more precise if you're actually running the numbers to calculate it, you at least have some sense if those are reasonable stress levels or not reasonable stress levels, right? And so that's where, again, these are our steps. We plot the stresses on the x face, then we plot them from the x prime face. That's what flips that tau xy sign. We then connect points 1 and 2. That locates the center of the circle. Now I'm calculating the radius of the circle, right? And once I've drawn more circle, I can then calculate the principal stresses. They're just sigma average plus r, sigma average minus r. And tau max is always equal to the radius, at which point I can calculate the angle of rotation that I need to go through in order to orient my cube in the directions of the principal stresses.